Tell us. We need to know the things and the stuff. Validate us. Yeah, true. This is why we record locally.
How about now?
Can you hear me?
Yeah, we can totally hear you. Yeah, I was. I had muted my mic for the last episode, and because I was playing an interview, but now we're
Okay.
back. Cool. All right. So you're in TwitchCon down in San Jose.
Yes, I am straight south-ish from you, and we're in the same time zone, but we are far, far away because the world is large.
Yes. And everyone needs to know that we don't have a lot of time today because you've got to get back to twitching. Yeah. So twitchy. But say hi to everybody. Give everybody hugs.
Hi, everybody.
No, at TwitchCon. But also everybody here. Yeah. Because I think Sky's there and
yeah.
Man, who else is
Nicholas, who's been with us since like day 0 of Astronomy Cast and was at our first meetup in Austin, is going to be here.
Oh, that's awesome. All right, and just to let everybody know, because Pamela is doing TwitchCon, we don't have a lot of time, so we can't stick around and answer any questions. Oh, Scott Manley's apparently there.
Cool. I will look for him.
Yep.
And Phoenix and Rux are here.
Oh, great. All right, let us begin. Tell me when you're ready to press record on your side. And I know the audio is kind of crappy. Pamela's going to record a nicer version of it for the actual recorded podcast. So
I'm talking to you through my cell phone using my earpieces so that there aren't hotel internets on the video's audio.
Yeah.
Okay, I am pressing record and the levels look good. Hello, Chad.
I'm also pressing record. Hello, Chad. All right. Let's get cracking. Here we go. Astronomy Cast, episode 503, Gravity Maps. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. I'm Fraser, Cain, publisher of Universe Today. With me, as always, Dr. Pamela Gay, the director of CosmoQuest. Hey, Pamela, how you doing?
I am doing well. How are you doing, Fraser?
Great. Hello from TwitchCon in San Jose. So I hope you have a great time there. Before we get any further, I just want to say, by the way, last week I said it was about to happen. Now it has actually happened. Our book has hit the shelves. October 23rd came and went, and now you can just go to a bookstore and buy a copy of our book. And here's the part that now many of you I know ordered copies of it. The sort of first versions, people are loving how it looks, all the photography, but nobody is reviewing it on Amazon. So we are the top-selling book. It's the weirdest thing. We're the top-selling book in astronomy and astrophysics on Amazon. Take that, Neil deGrasse Tyson. But there's like no reviews of the book. So if you've ordered a copy and you've got a copy in your hands, please take a moment and go to Barnes & Noble, Amazon, wherever you bought the book from, and please write a review. It's so weird to me. Like, I don't know. Did we do a good job?
Reviewing it on Twitter. I've seen the reviews on Twitter.
I know. But there's none on Amazon, so it looks very strange. It looks bizarre to have this book that's the top-selling book, and yet nobody is reviewing it. So anyway, please, I beg you, when you get a copy, go to wherever you bought it from, and please do a review. It means the world to us. What? 5 what?
5 stars.
Oh yeah, of course. Yes, and 5 stars. Well, I mean, Yes, by all means. Post an honest review and honestly rate it the 5 stars that you know it deserves. All right, let's move on. So the Earth looks like a perfect sphere, but down here on the surface, we see that there are mountains, rivers, oceans, glaciers, all kinds of features with different densities and shapes. Scientists can map this to produce a highly detailed gravity map of our planet, and it turns out this is very useful for other worlds too. Pamela, gravity maps. What is the technical term for a gravity map? Do you know that one?
I don't know how to pronounce it. Geodesy, I believe.
Yeah. I didn't know how to pronounce it either, so I wanted you to do it. But of course, I should have remembered. Pamela can't pronounce, so I hope someone is.
I read too much.
Is it geodesy, geodesic? Can you think about a geodesy?
This is where we need Keeper of Maps. Keeper of Maps can tell us how to pronounce it.
Yeah, geodesy. So someone please help us out with the actual pronunciation. But and you've probably seen these images. They look like the Earth, but the Earth is covered in like red and yellow and green and blue blobs. And that is this map. So what is this idea of a gravity map? What is a gravity map?
So I first learned about gravity maps when I learned about the asteroid that killed the dinosaurs. And what it is, a scientist walks around in the olden days, nowadays we also use spacecraft to do this, and measures the fluctuation in how much the Earth is pulling on their instrumentation and them as a function of position. Now, if you know how far you are from the center of the Earth and you know how much the Earth is pulling on you, you can calculate the amount of stuff between you and the center of the Earth. And as that amount of stuff changes, we will see the amount of gravity change. Now, what's cool is you'd think, hey, I'm the top of a mountain. There's going to be a whole lot more stuff between me and the Earth. And I work out the math. And yeah, I'm higher up, so I weigh less, but there's more stuff. And that's all true. But the other thing is you can be moving along a perfectly level surface and see the pull of gravity fluctuate as you walk over shocked, compressed former asteroid impact sites, as you walk over oil wells, as you change what is beneath you, the pull of gravity changes. And this allows us to map out the structure of our planet from the surface of the planet.
And it's pretty mind-bending that the instruments are sensitive enough that they can actually determine that difference in gravity. Like what kinds of gravity differences are they detecting?
Well, so what kind of got me when I learned this, I'm an astrophysicist. This is not a measurement I've ever made. I know there's super sensitive instrumentation in laboratories such that when it rains, you can measure the difference in gravitational pull of the mountains around you. There's a gravity lab up in Seattle that actually sees changes in their results when it rains. But what I hadn't realized is just how amazingly sensitive these instruments are in the field. People who are out there looking for oil have instruments that if you put them at your feet and then put them at your nose, you can measure the difference in the pull of gravity as a function of that distance, seeing the numbers change between your toes and your nose for how much gravity is pulling on you. That broke my brain.
Yeah. I mean, I think people just have no sense. That idea is amazing. You know, you can walk past a mountain and you're going to be experiencing gravity from the mountain. This idea that you're going to be experiencing gravity from rainfall is crazy. It's a really stunning of technology. So you are able to produce this incredibly precise map. What is it used for?
Well, as I mentioned, you're sometimes doing things like looking for oil. And You just lost my video.
Yeah, you've
So
paused. That's
sorry.
okay.
I'm
We're
Chad,
just
just
we're
gonna
just
have to.
staring at your face. It's fine. Keep going. We can
Okay.
hear you.
So I'm just going to ignore it. Okay. Sorry, Chad. So as I mentioned, people are out there, they're looking for oil, but beyond looking for oil, this is also an amazing way to map out things like past impacts into the planet Earth, where we've had, like, when the dinosaurs died, large rocks from space come in, large rock from space hits Earth, compresses the surface of the Earth. Over eons, it fills in with material to a certain degree, and you're left with not as noticeable a surface differentiation, but you can map out with gravity the rings and shock waves in the planet from that prior impact.
There was a great instrument that did this a couple of actually, it's funny. So like one of the first pieces of reporting that I did was back, I think 2001, 2000. It was this German experiment called, oh, was it Grace? There was but even before that, no, it was like SRTMM. I forget the name. I apologize, but it was on the space shuttle. The space shuttle launched with, it had the space shuttle, and then it had this boom that it or like a cable that it reeled out, and then it had this instrument at the end of it. And then as the space shuttle and this fishing rod, went over the Earth's surface, the two parts were experiencing a difference of pull, right? And so they were experiencing this force between the space shuttle and the probe that it had set out. And they were able to produce this incredibly detailed map of the entire Earth's surface, one of the most complicated ones that's ever been done. But there are now a bunch of instruments, a bunch of satellites in space that are specifically doing this. One European Space Agency has the Gravity Field and Steady State Ocean Circulation Explorer, or GOES. GOES, I think. GOCHE.
And then, of course, there was the Grail mission that NASA launched to map out the moon, which is a weirdo world with an asymmetric core, and we're able to map that out. And it's this double mission that gives us this extra sensitivity, like what you were mentioning with the fishing rod.
Right. Yeah. And so again, like the Earth is the place that's had its gravity map measured out the best, but as you said, the moon has experienced this as well, if you've got this kind of instrument. Let's talk a bit about GRAIL. So it's the Gravity Recovery and Interior Laboratory, and launched by NASA back in 2011. Is it still alive?
No, it is not still alive.
No.
But what was amazing about this mission is it's these two spacecraft, and they were maintaining contact between them and with the planet Earth, so they could very carefully, constantly update distance information. And they were measuring these slight fluctuations in orbital speed and how these spacecraft were orbiting, so that they could measure, oh, A has gotten pulled ahead towards this mountain range. Oh, now B is getting pulled ahead. And by looking at these slight differences caused by, hey, there's less gravity here, there's more gravity there, we're able to see a wavelength of light at a time, differences in how gravity is causing these things to orbit. And with the moon, the thing that I know a lot of us were just like, we knew that the center of mass of the moon was off center, but being able to see how radically different the side of the moon that we always see, the front Earth-facing side that's tidally locked towards us, is from that backside, both with gravity and with appearance, has led to changes in how we look at the formation of the moon, where there's new ideas that maybe the backside of the moon looks so different because it was splatted upon by a second smaller moon that failed to remain uniquely separate from what we have now.
Yeah, that's I just want to take a second and recap that too, because it is just really amazing. If you see what the far side of the moon looks like, it looks totally different from the near side. You don't get these beautiful seas and dark lunar mare regions. You just get, it's just pounded with impacts. And one of the ideas is that it used to have the moon. There was a second moon around the Earth, and at some point they merged, and that's why the two sides of the moon look so different, which is just just amazing. It would have been a crazy sight to see it happen.
And what's cool though is there's this essentially primordial, that's the wrong word because that goes too far back in time. There's essentially this original moonlit core that's in one location towards the Earth. And then we now have this spherical object with an asymmetric core, and trying to model that is all the scientific fun. And we can trace out the details with gravity.
And not only Earth and the moon have gotten the gravity map experience, I know that Mars has as well.
And this is where we're starting to try and figure out where might the land have been crunched under an ancient ocean. How has its history been hidden as dust storms sweep across the surface? And just like here on Earth, we're using new and amazing techniques to map out, well, Viking ships buried in cemeteries was a result that came out 2 weeks ago. We're not finding Viking ships on Mars, although that would be awesome. What we are finding instead is these differences in how the soil has been crushed under oceans, how it has been crushed under glaciers and rebounded over time, helping us understand what is there that we can't see that is structurally relevant to the history of Mars.
So with these gravity maps, they sort of serve as your first really big survey of a world to try and figure out where the large features are that are really interesting that you're going to want to explore. What are some places of unusual extra density, things like that. And then you can follow up with a more detailed mission that will explore some of these features more specifically.
And I can't stress enough how much this is the first step in what we're now calling multi-messenger astronomy. This is the idea that while we spent the first essentially 500 years of astronomy as a science looking at light, we now have the capacity to look at worlds, look at stars, look at, well, mergers of stars using, first of all, the light that we see with our telescopes. We look at the moon, we see the craters. We measure their heights using radar and LiDAR, reflecting light off the moon, but that's still light. Now we have this ability to also map things out with gravity, and this gives us a completely different view that allows us to see things that we otherwise couldn't get to pretty much any other way, because who's going to take the moon apart atom by atom to measure its density? And then on top of that, we start adding all of the particle physics where we're doing that's revealing water entrapped in the minerals. So we've entered this new era where light is just one tiny part of this, weighty story with gravity.
While you were talking, I was showing off images of Ceres' gravity map to the people who are watching us live. Again, Dawn was equipped with a way to be able to sense the gravity of the planet of the dwarf planet as it was orbiting around it. And so, one of the handy things about orbiting around a world is you can detect how its gravity is pulling and pushing and twisting and turning you as you're going around to produce this gravity map. And again, super fascinating for the geologists.
And this also allows us in complicated ways that I'm not going to try and explain because moment of inertia is mean. We can also start to get at the moment of inertia of different worlds. And that is a fancy way of describing labeling the mass that says if you have an ice skater with her arms out, she rotates slower. If you have an ice skater with her arms in, she rotates faster. And if you replace her bones with liquid, that changes how she rotates as well. Because solid, liquid, and gas all have slightly different ways of interacting while rotating. And that difference in how a can of soup versus a solid can of frozen soup, same mass, same density, different phase state, that difference in how they rotate is reflected in how worlds rotate and helps us get at, is there a liquid ocean? And so it's moment of inertia information that allows us to start thinking maybe even Ganymede has liquid ocean.
Yeah, it would be nice to come back to some of those other places, to Europa, to Enceladus, and perform very detailed gravity map measurements, because you have to be in orbit, and nothing has ever gone into orbit around Europa or Enceladus. And those are the big questions. We want to know, is there a place where is there liquid water closer to the surface? Although I wonder, can you tell the difference between liquid water and solid water with a gravity map?
No, but by combining information on how an object is rotating, which gets you the moment of inertia, with the gravity map, it allows you to start to piece together, okay, we have a map of this object's density that it only tells you the density between the center and the surface. We also have a map of roughly how it slishes in different ways from the inertia. And you get hints. It's not going to give you a detailed 3D structure. And this is where you start wanting to do things like we can measure more into the surface using sound waves reflected off, using radar reflected off. And with Europa, we actually have the chance someday with powerful enough instrumentation to just blast in with radar and start to get ideas of what's beneath the surface.
I'm just like checking out all of these places with gravity maps. I've been able to find a gravity map of Mercury as well, which thanks to Messenger, and of course Bepi Colombo is going back to Mercury now, has just launched, and so I'm sure will help add on to the gravity maps that are produced of Messenger. One thing that I always love, whenever there is a big earthquake on Earth, the geologists will tell us how much the Earth's rotation has changed because of how chunks of land,
the moment of inertia change.
Yeah, exactly. And so chunks of land have moved around. The actual shape of our planet has shifted, and that has changed the moment of inertia. And sometimes, the day length on Earth is slowing down every day, but every now and then you get an earthquake and it speeds up for a moment and then has to continue.
And, well, it actually stays sped up if things don't settle back the way they were. So the big Nepalese earthquake several years ago, which changed the height of Mount Everest, that massive earthquake changed forever the rotation of the Earth. Now, we can also change our planet in ways that change the rotation period of the Earth. The massive dam that was built in China on the Yangtze River that wiped out a ton of villages and archaeological sites also changed how our planet is rotating. So anytime you change the mass distribution, it changes the planet's rotation. This also means that massive droughts, massive flooding changes the planet's rotation. So our planet is always at the tiny fraction of a second level changing as we move the water around, as we move the land around. So the day is only 24 hours long with an error, and that's awesome.
Well, and you get these situations where, for example, as you mentioned drought, or you can have a situation where, say, a glacier will recede and the Earth's surface will bounce back up because it was being pushed down by gigatons of ice, and you get and again, geologists can measure, thanks to doing the gravity mapping. They can sense how much the Earth is responding to, say, having the weight taken off on top of it.
Yeah.
Again, just mind-bending levels of capability. Is there any kind of analogy to this at all in astronomy? So, when we look out into the universe, can we produce gravity maps of blobs of dark matter and things like that?
Yeah. So here, this is where it gets down to using microlensing instead. So instead of looking at how a satellite orbit is changed as it flies by or goes around a planet, what we instead look at is photons, which is still stuff. We look at how that photon, which doesn't have mass but does have inertia, how its path is changed as it goes past an object. And that change maps out the gravity of the object. When we look at gravitational lenses, we can see this background object was twisted and turned in this way, which means there's this shape of mass in between. This other one was shredded in this other way. That means there's this distribution of mass in between. This is how the Cosmos Project produced the very first three-dimensional map we've ever had of the distribution of dark matter. Is they worked off of the assumption that if you look at a bunch of galaxies and you average their shape, the average shape is a circle on the sky. And if the average is instead a teardrop, a dead amoeba, some other squished, not circle shape, that shape is a reflection of the intervening dark matter. And if you look at reasonably nearby galaxies and measure their distortion, that gives you one depth of dark matter. If you then look at slightly further away galaxies, that gives you the next depth of dark matter. And they looked at galaxies at a whole variety of distances, mapped out their gravity distortions from dark matter, and got us the shape of dark matter.
And one other thing, although I know it looks similar when you look at, say, the cosmic microwave background radiation, false colored images that they're producing, you're looking at these temperature variations. But don't the temperature variations of the CMB map to density fluctuations, and wouldn't that impact the gravity a
Somewhat.
bit?
So what you're getting at is a Zaniev-Wildovich effect. And that one I actually know how to say.
Nice.
So with the Zaniev-Wildovich effect, you have the cosmic microwave background radiation is getting redshifted as it passes through the massive gravity field of a galaxy cluster. And so the most massive galaxy clusters appear as holes in the cosmic microwave background because they're essentially shifting all of that light. It's a great way to find high mass objects that aren't giving off a whole lot of light by looking for the missing light of that background illumination.
And you're detecting it through its gravitational impact on the light that's coming from the birth of the
shifting the
universe.
Color of the background universe.
Oh, so amazing. Pamela, again, thank you so much. Have a great time at TwitchCon. I realized when I started, I forgot to mention the name of our book. It's the Universe Today Ultimate Guide to Viewing the Cosmos. Everything you need to know to become an amateur astronomer. And I know I mentioned it last week, but that's the book. So again, if you've gotten a copy, please do a review. That would be awesome. We'll see you next week.
It's a beautiful book.
It is beautiful, yeah. I'm really proud of it. All right, we'll see you next week, Pamela.
See you. Bye-bye. Okay, and now I'm safe. And you save. And we all save together.
We all save. Everybody save.
Okay, so while we are saving, we can probably take like one question before I get running.
Sure. Arjun asks, does the gravity map of the Earth change seasonally? Who can benefit from this data?
So the gravity map of any given place will change according to its seasons. Yes. So I mean, summer one place is winter another. So we have a constantly evolving gravitational map at the smallest scale. I'm not sure who can benefit from this. It's just something that in general you have to correct for. At the end of the day, it's not the gravitational effect of drought or flooding that matters. It's the lack or overabundance of water that matters. And then scientists have to correct all of our data in those places that are flooding or droughting or what's going on.
Right.
And today was 503 or 504?
Today was 503. Yeah.
Thank you.
And so you would, I mean, I guess the point is like during the season, you would see snow and ice moving different places, the mountains. Like if you can detect that the mountains are wet, you can detect rainfall and reservoirs filling up and emptying out and rivers flowing into floodplains and
where it really does matter is on the smallest scales. You can see motion inside of volcanoes this way.
That's crazy. All right. And then William Vanderbeek asks, are there any plans to map, he says the ice giants, but also like gas giants? Like, can you produce, I did some searching for that. I couldn't find any gravity maps of Jupiter and the ice giants.
And I can't think of any reason that they'd have structures within them. And so the lack of publication, to me, my stomach is saying, with a very well-educated background that hasn't actually looked this up, that the lack of publications reflects people looking and going, yeah, it's a sphere.
It's a sphere.
We knew that, and they're not publishing.
Yeah, no, I haven't seen anything.
But I don't know.
Right. I mean, you would, Cassini went around and around and around Saturn, so you would think that potentially it could have perhaps a more sophisticated probe whose only job was to determine if there's a gravity, to map the gravity map of one of those worlds. But Jupiter is so dangerous, you don't want to go anywhere near it for very long. All right. Well, Pamela, I know we've got to let you go. Thanks, everyone, for watching us live. Sorry for the short show. Get out there and represent astronomy amongst all those gamers. You're doing the good work. Thanks, Pamela.
Thank you.
See you next week.
Bye.